Hello, good people. Welcome back once again. My name is Richard, has never changed. So today we are tackling bonding and chemical interactions. This is one of the most heaviest and loaded chapter in the MCAT prep, especially the chemistry, which is the chapter 3. But we're going to try as much as we can today, to get through a lot of the stuff. I'll try to shoot just one video and maybe cut it into different sections so it is easier to watch. Now, introduction. Let's talk about introduction to this chapter. You know that when we started this chemistry prep, we first started with atoms, the structure of an atom. We learned about valence electrons. Then we learned about periodic chemistry, where the atoms fit on the periodic chemistry and combining these atoms to form elements, right? But now we are talking about how these atoms interact. So if you see it, it's like a trend, a very predictable trend. From A, we go to B, then we go to C. So in talking about how atoms interact and bond, they are, if not the most important, one of the most important phenomenon or concept in the world we live today. If it wasn't about how atoms bond or interact with each other, the universe might not exist. Especially for the way you and I know it, for it to be able to even support life in the first place. So let's go into it. Chemical bonding and chemical interactions. So when we talk about bonding, it is the interaction of atoms, right? Bonding is, so in simple terms, bonding is the interactions of atoms to form molecules or compounds or compounds. So how atoms interact with each other to form molecules and compounds in order for it to sustain life or for a natural phenomenon to occur. There are various ways in which atoms will interact with other atoms or with themselves. And these various ways are what we call bonding, right? So first of all, the bonding, somebody might ask, why do atoms have to interact with each other to form bonds? Now, the reason why atoms will interact with each other to form bonds is because the atoms want to be stable. They want to be more stable. They want to obey a rule in chemistry called octet, right? They want to obey the rule in chemistry called what? The octet rule. Now, oct is a number for 8. It means 8, which means that atoms would want to have 8 valence electrons on the outermost layer of that specific atom. When we was talking about periodic chemistries and or the periodic table and the trends, we said that the identity of an atom is basically due to its valence electrons. The valence electrons are the ones that partake in the bonding. And the atoms would want to be stable by filling their valence shell with 8 electrons. That detects stability. And that rule is called, or that theory, or that rule is called the octet rule. Now, the octet rule states that atoms would want to fill their valence shell, not electron, shell, with 8 electrons in order to be stable like the noble gases. So, and if you do remember from periodic table 2, we also said that the noble gases barely partake in any type of chemical reaction. Well, except some has, you know, a readable electronegative values, like the noble gas like xenon would form some bonds, but the majority of the noble gas wouldn't form no bonds because they have 8 electrons in their outermost shell, and then they are what? Stable, right? But this octet rule, the last time I said, it's called the rule of what? Thumb. It's called the rule of thumb. The octet rule is what? The rule of thumb, because there are more atoms that do not obey this octet rule than there are atoms that obey the octet rule. Why am I saying this? There are 3 ways in which an atom would not obey the octet rules. That is the exceptions to the octet rule. And by the time we go through these 3 ways, you realize that there are more atoms that fit in these 3 ways to disobey the octet rule than there are atoms that actually fall in this 8 rule chain. So the first one is incomplete octet. Incomplete octet. So some atoms would form an incomplete octet. Why would they form an incomplete octet? Because both physically and practically they cannot have 8 electrons in their valence shells, because they don't even have the shell in the first place to put the 8 electrons on. So they are stable with less than 8 electrons, and they are happy with less than what? 8 electrons. Now these atoms are the first 5 on the periodic table. So the incomplete octets are some atoms cannot physically, or however you want to put it, quantum mechanically, some atoms cannot physically put 8 electrons in their valence shell, in their valency or their valence shell. Why? Because they don't have the shells. They don't even have it to put the electrons on. And those atoms are hydrogen, helium, lithium, beryllium, and then boron. Just B for boron. So the first 5 elements on the periodic table do not obey the octet rule because they form incomplete octets. Why do they form incomplete octets? Because they don't even have the shells to put the electrons on. Now, if we take hydrogen, for instance, this is hydrogen, right? If you draw it like this, it's just this with 1 electron. That is hydrogen. If hydrogen gets one more electron to fill its shell, it is stable. It does not need 8. Now, if you go on to helium, helium is also like this, right? Helium is already stable. It has its shell filled. That is why we put helium in group 8 under the noble gases. Not because it has 8 valence electrons, but because its outermost orbital or its outermost shell is already filled to the maximum amount of electrons it can hold. And by the way, if you want to know the maximum amount of electrons a shell could hold, it is just 2n squared, where the n is the principal quantum number. So in this case, hydrogen falls under the principal quantum number 1. That is, it falls under period 1 on the periodic table. So if you want to know the maximum number of electrons it will hold, you just get 1 square, which would give you what? 1. 2 into bracket 1 square, which will give you 2. So that is the maximum that it can hold. Helium is also in period 1. That means it can also hold maximum of 2 electrons. Now, when we come to lithium, it is in period what? 2. So lithium is like this, and then 1 more shell like this. What is the maximum number of electrons helium can hold? The shell, because it is in the second period or the second principal quantum number, it is 2 into bracket 2 square. 2 square is 4. 4 times 2 is 8. So lithium would theoretically or numerically be able to hold 8 electrons because 2 square is 2. 2 square is 4, and then 4 times 2 is 8. But The reason why lithium does not hold 8 electrons in its outermost shell is because it has one here, right? It is energetically favorable, or it requires less energy to lose this electron than the energy it will require to go and borrow what? 7 more electrons from somewhere to join its outermost shell. So if you do it, it will go for both. Beryllium also theoretically could hold 8 electrons, but if you draw the structure of beryllium, and there you go over this 1, 2, 3. So 1, 2, 3, 4. 1, 2, 3, 4. When you draw beryllium like this, theoretically it will be able to also hold 8 electrons, right? But the reason why it doesn't hold the 8 electrons is because it is energetically favorable to lose these 2 electrons, to just give it away, than to go and get what? 6 other electrons. Boron is the same way, right? Boron is the same way. If you draw the structure of boron, it follows the same pattern, 1, 2, 3, like this, right? It is also favorable to lose these 3 electrons than to go and then borrow, than to go and then borrow 5 more electrons to make it what? 8. Now, when the second exception to the octet rule is what we call expanded octet. So second is what? Expanded octet. Call it expanded octet. Now, the expanded octet also says that elements that are above the period 3, or from period 3 going, elements that falls in the period 3 going, right, would also disobey the octet rule because they have a disposal of the d orbital or the d subshell. They have the d subshell at their disposal, so they can dance with electrons. They can form, or they can gain more electrons, right, than 8. So they could put more than 8 electrons in their valence shell. That is the expanded octet. So if you are reading on the periodic table and you go hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, right? So if you take sodium and magnesium out, because theoretically it will fall under the period 3, but it wouldn't have the p orbital at its disposal just yet, right? It wouldn't have the d orbital at its disposal. Sorry, not the p orbital. It wouldn't have the d orbital at its disposal yet. It cannot utilize it. But as soon as you pass magnesium going, it has the d disposal, the d orbital at its disposal, so it can fill it with more electrons. So let's say we pick an element, right? Like let's go to the periodic table and pick some elements. So if we take an atom like chlorine, right, that is in the period 3, and it has the d orbital at its disposal, right, we're going to have something like a compound like chlorine pentafluoride, right, ClF5. So chlorine pentafluoride, if you have the chlorine in the middle like this, it can bond to 5 other fluorine atoms, right? Putting 10. So each bond, we'll get here too, each bond is 2 electrons. Putting 10 electrons around the chlorine atom, because it has the d orbital at its disposal, and how many, it has the d subshell at its disposal. How many suborbitals, how many orbitals does the d shell has, right? So that will be d has 5 orbitals. So if you draw it, it's gonna be like the valence shell will be like this: 1, 2, 3, 4, 5, and then chlorine can put 10 electrons in here, right? So it can put 10 electrons in there and completely be stable and be energetically favored than putting something like 8 electrons. If you put 8 electrons in there, it will be like something like this. And there will be like 2 unpaired electrons causing some type of instability in the compound or the molecule. So that is the second rule for us, the expanded octet. So the expanded octet states that atoms from period 3 and beyond, right? So from period 3 going, period 3 and beyond can have more than 8 electrons in its valence shell. In its valence D, let's just put it in its valence D subshell, because it can utilize the D subshell like this. So when it utilizes it, it will form it will put more electrons than 8 in it. That is the third rule. Now that is the second rule. The third rule for violating the octet rule is odd number of valence electron, like odd number of valence electrons. So 3 is odd number of valence electrons. So odd number of valence electron. Now, what do we mean by the odd number of valence electron? Sometimes you might have compounds that would form, and then the combined valency or the combined valence electron of the compound is an odd number. If it's an odd number and the compound is just made out of 2 atoms, how are you possibly going to share the odd number equally among these atoms, right? And come to talk about it, even for one to even get 8 to complete its octet. So that is the odd number of valence electron. Because if you do have that, you cannot mathematically divide it without one atom having more electrons than the other. And by so doing, you put the atoms at the disposal of not having 8 electrons. And those atoms sometimes tend to be stable because, you know, the atom, the lone pair of the electron will be revolving in between these 2 atoms, causing some type of stability. So that is the odd number of valence electron for you. That also states that some atoms, right? Some molecules have odd number of valence electrons, and hence cannot divide evenly among its atoms or its component atoms. And those an example of such a compound is NO, nitrogen monoxide. It has valence electron of 11. So how is it possibly going to divide the 11 electrons between the oxygen and then the nitrogen? Now we will get into how to count the valence electrons first. I don't want us to get ahead of ourselves. So a little bit of recap. Bonding is how atoms interact with each other. Why would atoms interact with each other? So that they could be stable. Now, how do atoms determine that they are stable? That is if they have 8 shells in their valence electrons. And what is that rule called? It's called the octet rule. And now we've got to figure out that the octet rule has 3 exceptions. 1, the incomplete octet. 2, the expanded octet. And 3, the odd number of octet. And by going through these 3 rules, we have found out that there are more atoms that actually disobey the octet rule than there are atoms that favors it. So we are going to go into the types of bonds that an atoms would form with each other. Let me wipe this out. Now, for the sake of this chapter, we're going to go over just 2 types of bonds. That is the ionic and the covalent bond. Now, how are ionic bonds formed? Ionic bonds are formed when an atom of a very low electronegativity, especially metals, right, bonds with an atom with a very high electron affinity, or you could say a high electronegativity too. But to be practically and factually correct, just go with the electron affinity, right? The reason being that the atoms with very high electronegativity, what do we say about the atoms with a very low electronegativity, what do we say about them? Electronegativity is the energy required to remove 1 mole of an electron from a gaseous atom. So when we are removing the electron from a gaseous atom, if the energy that we require is very low, that means the electron is not being held in place very strongly. Hence, the atom even want to get rid of that electron. So by so doing, we don't require a lot of energy to yank out the electron. Now, once we do yank the electron, we bond with an atom with a high electron affinity. What is the electron affinity? It is the energy change when you add 1 mole, or is the energy release when you add 1 mole of an electron into a gaseous atom, right? So the higher the energy release means the more the atom wanted that electron. So when we put the electron that we just yank out from the low electronegativity and we give it to an atom that has a high electron affinity, right, it creates a bond. And this bond is called ionic bond. Now, put in mind that in ionic bond, we yanked out an electron and gave it to one person. We took it from one atom and gave it to another atom. So it's complete transfer of electrons, right? So ionic bonds is the complete transfer of electrons, right? Electrons. When a low electronegativity, I'll just use En, electronegative atom, right, bonds, into bracket, it will transfer its electrons, right, bonds with a high electron affinity atom, right? So the low electronegativity atom are usually metals, the group 1 alkali and then the group 2 alkaline earth metals, bond with the and then the ones with high electron affinity are the halogens, right? So let's say into bracket the halogens. The halogens. Now, when these are formed, right, let's say we have an atom here, like let's say sodium. We have sodium over here. Sodium is the 11th. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have one over here, 11. This is a stable sodium atom, right? Like a sodium atom, a neutral sodium atom, and chlorine. We put chlorine here. So let's say we have chlorine, 17. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So this our chlorine atom here, right, have 7 electrons in its valence shell, right? And then it is close to the halogen, the noble gases. So if it would want to get one more electron, it is energetically favorable if it just gains 1 electron to add to this already 7 electrons to complete the octet. That makes it have a high electron affinity. Sodium over here has what do we call it? Has one valence electron that it wants to get rid of, right? So that it will be stable. It will also attain the octet. Then it will have 8 in its valence electron, and that makes it become low electronegativity. So sodium here will completely transfer this electron to the chlorine atom. So this electron would complete transfer. So complete transfer. Let me use a different pen marker. This one is a complete transfer to the chlorine atom. So when they transfer the atom to the electron to the chlorine atom, what happens is that it creates charges, electrostatic charges, right? Making this sodium to become more positive, right? And making this chlorine become more negative. Now the charges that it just created, right, attracts each other, and thereby the bond is formed. So that is how ionic bonds are formed. And when ionic bonds are formed, they usually form crystal lattice, because like if you take a sodium chloride salt, which is a table salt in its nature, the salt itself there is fairly neutral. It cannot conduct electricity, right? So how is it there just fairly neutral and it's not charged? There are charges in the various bonds, but then it is not charged because it forms a crystal lattice. And how a crystal lattice is, it's a 3D arrangement, right, of the various atoms that is in it. So let's get like a 3D arrangement over here. Oh shoot. Okay, so now let's truly dive into this. What compounds can actually, or what atoms can actually form nonpolar covalent? Means if you are going to form a nonpolar covalent, it means that you don't have any electronegativity differences. It has to be the same electronegativity or a difference that is as low as 0.5, which could be barely get on the periodic table. So the compounds that forms like, diatomic molecules like the halides, they are all nonpolar, right? So the atoms that could go in the way of, let's say, oxygen gas, nitrogen gas, fluorine gas, something like that, iodine, iodide gas. See, these two, the diatomic halides, they form nonpolar, and if you look on the periodic table, they form a number 7, and it's 7 of them. But I only remembered 4. They form a 7. They go oxygen, nitrogen, fluorine. Then it comes down to chlorine. Then it comes down to iodine, or maybe it comes down to something else before iodine. Then it goes down there. It forms a 7 on the periodic table. They form nonpolar covalents because when they bond with each other, let's say oxygen has electronegativity of say 2.1. If it's bonded with another oxygen, it will also have electronegativity of 2.1, meaning the difference will be 0, right? So there will be no form of polarity whatsoever. That's why they are called nonpolar covalent bonds. Now for the covalent bonds, the polar covalent bonds, the electronegativity difference is said is in between 0.5 and 1.7, and they are on equally shared electrons. So if anything bonds with each other and it is less than 1.7 but greater than 0.5, it is polar covalent. And how do you determine polar covalent? We will get there, because sometimes you can not just memorize the electronegativity values of the elements. You have to figure it out. And one thing is that when you are figuring it out, what if an atom is polar or non-polar, it will not determine on the let's say the electron structure, the electron geometry of the atom. It will depend on the molecular geometry and the sum vectors of the charges. So if you have an atom, right, that has if you have an element, or let's say in this case a molecule that has some sort of polarity to it, if you sum up the vectors and it gives you 0, is non-polar. But if you sum up the vectors and the vector sum results in some type of a number, then it's a polar. We will get to the vector sums of these things so that you get to know how to determine the polarity. And for coordinates, covalent bonds, for them, as usual, just one of the bonding species. I said species because it can exist between two molecules, two ions, two radicals, an atom and an ion, right? Something like that, whereby just one of their pairs is bringing a shared pair of electrons. And these coordinate covalent bonds give rise to what we call Lewis acids and Lewis bases. You say Lewis acids are what? Electron pair donor, right? So they will donate electrons. So anything that would bring electron in a covalent bond is a Lewis acid, a Lewis acid. And then the base is electron pair acceptor, right? So the other species that is just there accepting the electron would be the Lewis base, right? So in that situation, beryllium fluoride and ammonia. In that situation, if you have compound like beryllium fluoride, right, BF3, right, and then ammonia, NH3, right, the beryllium fluoride will bring the lone pair of electrons to be shared, right? So when it brings the lone pair of electrons and it bonds like that, then we have the bonds that will form between the beryllium fluoride and then the ammonia. And in so doing, we get ourselves a coordinate covalent bonds structure. See, in this case, it was between a molecule and another molecule. You get it? So that is how those things goes. And this is going to give rise to our next topic of discussion, Lewis structures. Lewis structures. Now, when we talk about Lewis structures or Lewis dot diagram, they are basically a representation of an atom using its valence electron. That's basically what it is. We are representing an atom using its valence electron. And once when we study the periodic chemistry, we said that the groups are the valence electrons. So if you pull up the periodic table on your MCAT, and let's say you get to an atom like nitrogen. So when you pull an atom like nitrogen, which is in group 7, N, you just surround it with 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. That's it. Oxygen, group 6, 1, 2, 3, 4, 5, 6. So since Lewis structures is just a representation of an atom by its valence electron, whereby we use dots to surround that atom as the valence electron, we can also use it to represent a compound or a molecule. So let's say fluorine, for example, right? Fluorine would have 1, 2, 3, 4, 5, 6, 7, right? And will have 7 electrons in its atomic shell. And for a fluorine ion, which is like the F minus, would be 1, 2, 3, 4, 5, 6, 7, 8 to fill the octet. So if we want to represent the fluorine halide, which is the fluorine diatomic gas, or the fluorine gas, the F2, we are going to have like the F 1, 2, 3, 4, 5, 6 dash, another F 1, 2, 3, 4, 5, 6, whereby the dash in between here represents 2 electrons that is involving in the bonds. Understood? So if you are counting the valence shell of the electron, it's going to be 1, 2, 3, 4, 5, 6, 7, 8 for this fluorine. It's basically like when you draw a Venn diagram like this, if you are done like algebra or basic mathematics like this, this is the one F, this is another F, and this is the bond in between them. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And the bond is between them. So the bond is shared. This is the intersectionality of the bonds. Same thing that happens over here. So once that is clocked in, there are some rules that needs to be followed when you are drawing Lewis dot structures. I believe there are a couple of rules, 3 rules. But first, Lewis dot structures are representation of species. I use species because you can substitute it for molecules, ions, atoms, compounds, whatever. They are all different species, right? Representation of species using dots, right? To represent, I'll do it to rep the valence electrons. Lewis. Sorry, people. I am as I told you earlier, I'm not a teacher. Don't have a major in education. I'm not in medical school. I'm just trying to get into medical school. So the best way for me to learn is to teach. This is an empty classroom. There is nobody here. I'm just teaching myself this, and I'm recording the video and post it online. Whoever watches it or find it helpful, mashallah, thank you. If not, mashallah, thank you. Yes, so that would be the Lewis definition. Now there are rules, and when you are drawing the Lewis structure, rules in drawing Lewis structure. So there are rules when you are trying to draw the Lewis dot structure of any compound or any species. I'm going to use hydrogen cyanide, HCN, right, to demonstrate how these rules are applicable. So rule number 1 is draw the backbone of the species by putting the atom with the least electronegativity value in the center. Right? Now, HCN, right? You say which one has the lowest electronegativity? Technically, it is hydrogen, right? But what you wanna put in mind as a rule of thumb is that, or not as a rule of thumb, as a nuance or an exception, right? Except, so this thing is except for hydrogen, right? And the halogens. These always goes to the sides. They always go to the sides. So in this case, I know that carbon has the least electronegativity on the board, but sometimes if you face the difficulty where you cannot tell the electronegativity, go with these things. So in that case, it's going to be H, C, and then N. Rule number 1 is done. Rule number 2 is draw single bonds in between them. or just put lone pair of electrons in between them. It's interchangeable. So what I do is I draw a single bond in between them. That is rule number 2. Single bond, single bond. So rule number 2 is single bond in between. Now rule number 3 is you count the valence electron of each of the atoms in their neutral states, right? And then you add them up. After you add them up, the sum total will be the valence electron for the entire molecule or compound. So you count each valency, let's say valency of the individual neutral atoms. That's right. The sum total of these is the valence electron. Is the valence electrons of the entire species. So I'll come over here. I'll continue over here. Big arrow. So what species do we have? We have our hydrogen, we have our carbon, we have our nitrogen. Hydrogen is in group 1, so it has a valency of, it has 6 electrons. Nitrogen here is in group 7, so it's going to have 7 electrons. So when we do sum these together, we're going to get the valency. The valency is equals to 1 plus 6 plus 7, which gives us 14. So our valency is 14. Now, the next rule is that once you have your valency, start putting lone pairs of electrons in the next highest electronegative atom to complete its octet. So put the valence electrons around the highest, or the next one with the highest En to complete octet. What is the octet? The 6. So in this case, this H, C, N. Now the N is the one with the highest electronegativity. It already has 2 electrons here. We need to complete its octet. Octet is 8, and then it has 2, so we need 6 more. So we go 1, 2, 3, 4, 5, 6. Now next we move to hydrogen to complete the octet of hydrogen. But over here, hydrogen has a complete octet. Why? Because hydrogen can theoretically just has only 2 electrons. And it already has the 2 electrons over here. One is here and then one is here, involving in the bonds. So what do we do next? We surround the remaining electrons on the carbon atom, right? As a lone pair on the carbon atom. So 1, 2, 3, 4, 5, 6, right? That we do have 7, 8, 9, 10. How many electrons are left? 4 electrons. So you put 2 here and then 2 here, right? But since the atoms like this, or since species, which is a molecule like this, it's not energetically favorable, they don't really want lone pairs of electrons, keep on drawing single bonds between these ones until you exhaust the lone pairs that surround the carbon atom. So in that case, let's come over here. So we are going to draw until we exhaust it. So structure 1 is going to be HC 1, 2, N. And then in this case, we'll have just 2 here. And then we have 1, 2 here. The ones down here and this one's down here. Oh, let me use this one. Down here were used in a bond. Those lone pairs were used in a bond, right? And then the next one is going to be like, the next one is going to utilize, which is structure 3. That was structure 1. So this is structure 3 is going to utilize this. 1, 2, 3, because the lone pairs is still not exhausted, and we're going to have 2. This one and this one are involved in this bond. So that is how you draw a Lewis-Dot structure of a compound. If there is a mistake that I've made in a place, let me know in the comment section. So when you do this, it brings forth, right? It brings forth different structures that can be drawn for the same compound, right? See, this is still hydrogen cyanide. This is also hydrogen cyanide. This is also hydrogen cyanide. And what do we call the structures? The same structures that can be drawn for the different structures that can be drawn for the same compound is called resonating structures. Resonance or resonating structures. Right. So the technical definition of a resonating structures, or the factual definition, is that they have the same bond connectivity, right? Is atoms that have the same bond connectivity but difference in the arrangements of the bonding electrons. That is resonating structures. Now, if it has okay, so resonating structures is defined as they have the same bond connectivity. The same. Hydrogen is bonded to carbon, carbon is bonded to nitrogen in each case, right? They have the same bond connectivity, but difference in the arrangement of the valence electron. So or the bonding electrons. So in this case, the bonding electrons are arranged in different ways. Those are resonating structures. And opposite to resonating structures is what we call isomers, right? We are not going to talk a lot about isomers, but if the bond connectivity is different and the orientation of the bonding electron is also different, is called isomers. Resonating are the same, they are still the same molecule, right? They are still the same molecule or the same compound, it has not changed. Resonance, isomers on the other hand are different compounds altogether. Even though it has the same atomic composition, as it will be maybe a hydrogen and a cyanide and a nitrogen in the same atom, right? It has different connectivity. That maybe in that case, hydrogen is now bonded to carbon, it's probably bonded to nitrogen, right? That is what brings us isomers and resonating structures. So the resonating structures is like different molecules all together, right? Now, hydrogen cyanide, as we do here, they are in real life, right? The structure of hydrogen cyanide is anywhere in between these three resonating structures. Just like when we did isotopes, that we said that it's just the average, the weighted average. The same thing applies to resonating structures. It's the weighted average of which structure is more stable. In this case, this one, the third structure is more stable. So you're going to see it a lot. But then at any point in time, if you were to grab hydrogen cyanide, it might have this type of bond also in it. But you're going to find this one more because it is what? More stable. So those are the introductions to a Lewis-Dot structure. Formal charge. Now, in any MCAT question, you can be tasked to calculate the formal charge on the central atom or the subordinating atoms or the bonding atoms. Now, if you want to calculate the formal charge, there are three ways that you could go about it, right? The formal charge, number one, could be the difference, right, between the valence electron of the neutral atom, right? The neutral atom and the atom in the bond. Let's use HCN again. HCN again. So this HCN, if you are tasked to find the charge, the formal charge of nitrogen, for instance, it will be the difference between the valence shell of the neutral atom, which is nitrogen has 7 valence electrons, and the bonded atom, which is 8 in this case. And that will give you at 1 plus 1 or minus 1. But this is just a nuance. Refrain from using this, right? The second one that you could use, right? The formal charge, let me just use it FC, is equal to the valence electrons, which is V, minus into brackets the number of non-bonding electrons, right? Non-bonding E, plus half of the bonding electrons. This is what you can find. So let's use nitrogen again, for instance. The valence of nitrogen is 7 minus into bracket its non-bonding. Let's use like this version of the nitrogen, right? So if we are finding the charge, the formal charge on this version of the nitrogen, its non-bonding electron is 1, 2, 3, 4, 5, 6. So 6 minus half of plus half of its bonding electron, which is 2 bonding electrons, so 2, right? So in that case, this will cancel that, and then we have 7 minus 6, which will give you 1. See, it wasn't far off from when we use that. We also got 1. But another trick that you could also use, the third way of finding it, is the formal charge is equals to the valence electrons minus dots minus dashes, right? Minus dots minus dashes. So you pick the valence electrons, right? How many, and if this is what we are looking for, how many dots does it have? 1, 2, 3, 4, 5, 6, right? Minus dashes, 1 dash responded to that, and you still get it. So for the nitrogen, for this version, the valence electron is 7. How many dots? 6. How many dashes? 1. So we get still -1 for these. Oh, it's positive 1 for those. So that's how you could go ahead and then calculate your formal charge, right? We are going to pause here, and then in the next video we are going to do